Hello everyone and welcome to the course on simulating fluid flows using Python. I hope you all are doing good and are up to date with the content that we have looked at so far. So we have looked at various kind of numerical schemes to solve the convection diffusion equations. We have looked at the central differencing, upwind and the hybrid schemes. So if you recall, these all are either first order accurate or second order accurate schemes. And that is why today we are going to have a look at the quick scheme. So I'll first introduce you to what the quick scheme is, what the methodology and the fundamental principle is. Followed by that, I would talk about the discretization. And we would see that, not very formally, but quick scheme is a third order accurate scheme. And that is why it becomes very important for a CFD learner to get an idea of how you can use the higher order accurate schemes. And especially if you have used any commercial packages such as ANSYS Fluent, for example, you might have seen quick in the drop down menu whenever you wanted to give the solver properties into the problem. So from that perspective as well, it would be very beneficial to learn about the quick scheme. So without wasting any further time, let's get started. So before jumping into the quick scheme, we would like to have a small recap of what we have covered so far. So we had looked at the central differencing scheme where we saw that it was second order accurate in space, which was a good factor, but there were some boundedness issues at high value of Piclet number. And in order to resolve that, we introduced the upwind scheme through which we saw that there were no boundedness issues whatsoever. However, the downside was that there was a first order accuracy in space, and the same thing was valid for the hybrid scheme, which was a combination of central differencing and the upwind scheme. And we saw that if the Piclet number is high, because it resorts to upwind scheme, so the first order accuracy still retains, even though both of these schemes are bounded by their own nature. Another downside of using pure upwinding schemes are that these schemes are prone to false diffusion in multidimensional problems. So we would talk about false diffusion when we would discuss 2D convection diffusion problems, because false diffusion is a phenomena that happens in multidimensional systems such as a 2D system or a 3D system. So roughly it implies that the governing scheme is capturing some extra diffusion or some fake diffusion. That is why it is called as false diffusion, which is not there in the problem. So for example, if we think of a pure convection problem, we know that there should be no diffusion of the fluid properties. But if we use an upwind scheme in a 2D or a 3D pure convection system, we see that the solution, it exhibits diffusion like variations in the final output. So that is what we refer to as false diffusion. So you don't have to worry about it right now, because things might not make sense in 1D. So that is why I am keeping that topic up for when we discuss the 2D or 3D problems. So this was about the kind of schemes that we have discussed so far. So let me talk very briefly about some higher order accurate schemes which are very commonly used in CFD world. So the first of them is the quick scheme, which stands for quadratic upstream interpolation for convection kinematics. So from the name you can notice a couple of things, that the word quadratic is used. So you can expect that we would be dealing with some quadratic system, be it a polynomial, in whenever we would talk about quick scheme. Then the second term is upstream interpolation. So again you can observe that it has some similarities in the name with the upwind scheme, and you would see that why this upstream interpolation would be useful in order to understand how the quick scheme works. And the last bit is the convection kinematics. So if you recall that until we were talking about the pure diffusion problems, the central differencing scheme itself was alright. There were no issues regarding boundedness or transportiveness. But as soon as we introduced the convection term, the central differencing scheme started to struggle, and we saw that that particular term was causing all the issues. So all the effort in CFD is towards handling that convection term, because that's a non-linear term in the governing equation. So the quick scheme is another effort to mitigate that problem, and that is why the name convection kinematics, it comes into the problem. So that is about the quick scheme here. And the second kind of schemes that are also used in CFD is called as the total variation diminishing schemes, or sometimes just called as TVD schemes. And there are many different kind of these TVD schemes which you can refer to in the textbook that we are referring to so far, that is the Versti and Malala Sekra. So in these series of lectures we would only narrow down our discussion to quick scheme, and the reason being that it is one of the most widely used scheme, and we here want to give a glimpse of the higher order accurate schemes, because our focus is on understanding how to write the codes in Python and how to write the basic solvers, not really very advanced solvers as of now. So let us start our discussion on the quick scheme. So first let us understand what is the underlying working on the quick scheme from a one-dimensional convection diffusion perspective. So we have our governing equation here, we have the convection term on the left, we have our diffusion term on the right. So if you recall, we were considering a mesh something like this. So we had west, our point of interest P, and a east node point, and we had a finite volume around it, and following that we had a west face and a east face. Suppose my flow direction is from left to right, that is from a Cartesian system, we have a positive u velocity here. And if you recall that we only need to modify the ways in which the convection terms are discretized, and I hope that you are able to understand or answer this y part that I was talking about just a couple of minutes ago. So using the quick scheme, we modify the way in which we define the phi e and phi w. So why this phi e and phi w is coming into the picture? Because if you look at the convection term, and when we would integrate this convection term over this finite volume, we would be left with rho u phi at the east face minus rho u phi at the west face. So phi at east face and phi at west face would come into the picture, and that is why we are after a modified definition of phi e and phi w. So recall that in the central differencing, this phi e, phi at small e, it was the average of phi at capital P plus phi at capital E. In the upwind scheme, it was simply the value at the upstream node, and in the quick scheme we would do something different. We are trying to see what we can do differently in order to retain a lot of properties that were exhibited by the upwind scheme, and we can get a boost up in the accuracy. So let us see how the quick scheme handles that. So alright, let us first look at the west face here, and a couple of things. Here we have assumed that the flow direction is from left to right, that is u is greater than 0. So I've made a few changes here. I have written these points P and W, that is capital P and capital W as it is. We have the small w as the west face of the control volume, and I have another grid point here, that is capital WW or west of west. So we'll talk about it as and when I'll discuss more about it. So in order to understand how the quick scheme works, again we look at the flow direction. So the flow direction is from left to right, and we are interested in this point small w. So if I am standing here and I know that the flow is coming from left to right, we can see that the point W or the capital W node is the upstream node, the capital P node is the downstream node. I hope that is clear. So if this is my small w, this is capital W, this is capital P, and the flow is coming this way. So in the general term, in the general English term, in the literal sense, we say that the flow is flowing left to right, flow is flowing upstream to downstream. So this point W, capital W is the upstream point, the capital P is the downstream point. I hope everything is okay so far. So now we have got this upstream point here and we have got this downstream point here. So previously we were focusing our discussion only until here, but quick scheme takes it a step further. So quick scheme says that we need two upstream points and one downstream point. So if this is my first upstream point and this is my second upstream point and this is my downstream point as usual. I hope that is clear. And the reason why I have drawn this vertical line would be very clear shortly. So now we have 3 points, we have 2 upstream point and 1 downstream point. Then the quick scheme says that we have to fit up quadratic polynomial of phi or for phi in these 3 points over here. So we can have a polynomial of a form ax square plus bx plus c. So that is a standard quadratic polynomial that we are going to fit through the 2 upstream point and 1 downstream point. So you can see that we have 3 points, we have 3 coefficients a, b and c, and we have 3 unknowns and 3 known values therefore. So what I am doing now is, in order to get the values of a, b and c is, I assume that temporarily I assume that this point is the origin here, and if my grid spacing is uniform, that is if this spacing between ww and w is h and ww and capital P would be 2h correspondingly, then I can have 3 different boundary conditions that at x equals to 0 my phi is phi ww, at x equals to h, that means this particular point here, my phi is phi w, and x equals to 2h, my phi is phi at capital P. So you don't have to assume that the origin is at ww, you can also take the origin anywhere you want. You can take the origin at, for example, the west node point and then say that at x equals to minus h the value is ww, at x equals to plus h the value is phi p, and x equals to 0 the value is w. So it doesn't really matter where you shift this temporarily origin. The only difference is your a, b and c would be different, but that wouldn't affect your final answer, and I'll show you why. So now since we are interested in this west face over here, so from this origin the west face is at a distance of x equals to 3h by 2, because this is h by 2, so this becomes 3h by 2. And if you would evaluate this particular expression after using these boundary conditions, you would obtain this form over here, that there is a weightage of 6 by 8 from the upstream point, there is a weightage of 3 by 8 from the downstream point, and there is a weightage of negative 1 by 8 from the second upstream point. And the same relation would hold true wherever you would put up your origin. You can have your origin anywhere, even away from this points here, but it just makes it simpler or more difficult if you change the origin. So you can try it, you can have the origin, let us say at point P or point W, and see if you get the same relations. Mind you that this particular relation is only true if the velocity is in positive direction. We will see what happens if the velocity is in negative direction in a little while. But before that, we also look at how the east face would be obtained. So this expression is for phi at small w, and similarly we want an expression for phi at small e. So using the same ideas here, so this is my east face over here. So again, if the flow is in the positive direction, the immediate upstream point is capital P, the immediate downstream point is capital E. So we need another upstream point that would become capital W. So remember, 2 upstream point, 1 downstream point, 3 points in total, that means 3 known values of phi. For polynomial we have ax square plus bx plus c, so 3 unknowns. So 3 known values, 3 unknown values, that would give us the a, b and c, and then depending on the location of your east face or the west face or whatever face that you are trying to evaluate, you can use the same quadratic polynomial to evaluate that property. I hope I'm making sense so far. I'm trying to be very gentle and very progressive in my discussion on this topic. I hope you are able to make sense. If not, please pause it here and try to watch that same ideas again. If you still don't get it, please write it down in the comments and I will try to give you a text description of what I'm trying to say. So now we have these 3 points here, and I have taken my origin at point W. So again we take the expression ax square plus bx plus c, and we use these boundary conditions here that at x equals to 0 phi is capital W, at x equals to h phi is phi p, and x equals to 2h phi as phi at e. So the reason why I'm taking the origin at the leftmost point is because I'm little more comfortable in dealing with these positive numbers rather than having minus h or minus 2h in my equations. So this is just a personal preference, but as you would see that if there are 3 points or 4 points in the scheme, these square terms that would become larger in numbers. So I have to square 2h, that becomes 4h square. So that is my personal preference to deal with those higher numbers on the expense of not dealing with the positive and negative signs. So you can try it either way yourself. So now we have this particular scheme here, that we have ax square plus bx plus c, 3 unknowns and 3 boundary conditions. That gives me the value of a, b and c. And again, just like previous, we can obtain phi at small e from this again by evaluating at x equals to 3h by 2. So from my origin here, this east face is lying at a distance of 3h by 2, and again if you observe, the kind of formulation that we get is 6 by 8 weightage is given to the upstream point, 3 by 8 weightage is given to the downstream point, and negative 1 by 8 weightage is given to the second upstream point. And this holds true in all the directions in the quick scheme, and you can write similar expressions if you have a multi-dimensional system as well. So now this is about the positive velocity side of things. I'll give you a glimpse of how this system would modify if we have negative velocity. So let us say we have a velocity in the negative direction now. So if I look at the west face here, so point P is the upstream point, point W is the downstream point, correct? And then point capital E would be the second upstream point. So using these 3 equations, I can write down the 3 unknowns and 3 knowns such that my origin is here, for example, and then I would seek the value at x equals to h by 2 to get the west face phi. And similarly, when we talk in terms of the negative u velocity for the east face, again if I stand here, the upstream point is capital E, the downstream point is capital P, and the next upstream point would be EE, that is east to east. So you can already getting a hint that we need more points in the stencil, or we need more points around our finite volume if we want higher order accurate schemes. So we have already covered like 5 points, WW, W, P, E and EE, if we want to make a general model. So if in general, this is true for all CFD systems, that in general if you need more accurate numerical schemes, then you need to have more points in your numerical scheme or numerical stencil. So you can recall that when we were talking about finite differences, the same thing holds true, that if we include more neighboring points, the differencing scheme was less prone to numerical errors. So I hope that this discussion would give you an idea of how to use the quick schemes. So I'll try to summarize again with the discretization as to how we use this particular knowledge. So again, if we go back to the equation that we had looked at, that is the convection diffusion equation for a positive u velocity, we know that using the Gauss divergence, after integrating on the control volume, we get an equation of this form. So we don't really need to worry about these diffusion terms. We are still handling them the same way as we were doing them in the central differencing. The only problem is the only modification is regarding these left hand side term, that is phi at small e and phi at small w. So you can observe that if I plug these numbers, or if I put in this rho into u into a, or maybe the areas can get cancelled out if they are uniform, so that I can put them, squeeze them down in this f term. So rho into u, that becomes my f at small e, and I can substitute for phi at small e as this particular expression here, and similarly rho into u evaluated at the west face becomes f of w, and phi at w can be expressed by the expression that we have looked at before. And the right hand side, it would simply becomes, so my gamma and delta x can be accommodated in this diffusion coefficient, that is d at small e, and then the gradients can be written in phi e minus phi p, and the similar for the other term. So we are not modifying the right hand side. The right hand side still assumes that the phi is varying piecewise linearly in the system, and that is why the gradients are expressed in the linear form. this is not a restriction. This is how the quick scheme was originally defined. You can also take the quadratic polynomial there, take the derivative, but that would make the system a little bit more complex. So quick scheme was originally introduced only for the convection term, and somehow that seems to work just fine. So now if we look at this equation, it is easy to see that we have a lot of phi p in the system which we are after. So we can rearrange this equation in this form, that is AP phi p equals to AE phi e plus AW phi w, and we would have one extra term corresponding to this phi ww that I am calling as AWW phi ww. So this is for the case when the u velocity is positive, and the same thing would you can have a similar kind of equation when the u velocity would be negative. And if you remember that if the u velocity is negative, then you can have the AEE phi EE in the system. So for that particular case, you may not have this AWW phi WW, and this would indeed be replaced by AEE phi EE. So to give out a general form, we can write a general equation that is a discretized version of the numerical scheme for this quick scheme setup is AP phi p equals to AE phi e plus AEE phi EE plus AW phi w plus AWW phi WW. So in the general setup, you see that there are 5 different points that we need to consider in order to write a quick scheme based solver. And here the coefficient AP again is the sum of all the neighboring coefficients plus the divergence of velocity, that is FE minus FW, and which generally is 0 itself, but we are writing here for a general system. So now I'm not going to derive all these coefficients because these are very readily available in the textbook of Versteeg and Malala Sekra. So you can have a look at this particular table that is given in the textbook itself. So here you can see some scary looking expressions, but this is the reason because we are looking at a very general expression. So we have some of these alpha things coming into picture, and the reason is because if the flow direction changes, the coefficients would change itself. So for example, if the flow direction is positive, AEE would be 0, and if the flow direction is negative, AWW would be 0. So these general coefficients, they take into account this variability of the flow direction, and that is what makes the higher order differencing scheme a little bit more tricky, because we need to take into account all these different parameters. And as we would see in the two-dimensional system, when we talk about a quick scheme based solver, that these schemes are fine in the interior of the domain, but as we come near the boundary, it becomes even increasingly difficult to adopt the boundary conditions for them, because again, if we need 2 extra points near the boundary which we don't have, we have to do some approximations there. So we would see about those complexities later on. I'm just giving you a heads up as of now. So this particular lecture also effectively concludes the discussion on 1D convection diffusion problems. The reason why we are not having these codes for these quick scheme is because we are going to have a look at them in the 2D system from a perspective of false diffusion as well. So in the next lecture onwards, we would start talking about the 2D convection diffusion. Again, we would revisit all the schemes. We would start our discussion from the convection diffusion, central differencing, then the upwind scheme, and we would look at this false diffusion stuff when we would talk about the upwind scheme, and then we would see how the quick scheme is able to help with that. So I hope that these lectures are keeping you entertained while learning CFD. If you have questions, please feel free to write them down in the comments of any of the videos that we have looked at so far, and please hit that like button if these videos are helping you out. Until the next lecture where we looked at the two-dimensional problems, please go through all these lectures, because these would give you a heads up in order to what we are going to discuss in those next videos. Until then, please stay safe and take care. I'll see you in the next one. Bye bye.